So, we have come to the lecture 33. In the last lecture, I talked about the effects of flooding. Till now, we studied one major thing we did in the last 10 or 15 lectures is we have been studying the effects of trim, the effects of trim. We are finding out what are the effects of trim, effects on trim due to a different phenomenon. We studied how the trim of a ship changes. So, first of all, we studied the what is trim, and we talked about the different factors that affect trim, mainly how the draft forward and aft are different and how it changes with respect to some phenomena that occur. The main reason for which is a change, seems to be a change in the volume at any point. So, we talked about different conditions like change in the density of seawater that produces a change in the volume, removing or what we call as discharging masses, or the adding of masses to different points of the ship produces a change in the trim of the ship. And similarly, a shift in the mass of the mass anywhere in the ship. For instance, if there is a shift in the ballast from, let us say, an aft tank to a forward tank, if there is a shift in the ballast or some fuel in some form, that also produces a change in the trim. So, these all produces change in trim. We quantified these processes. We saw what are the different formulas and mathematical expressions for the different processes, like provided you are given the initial trim and some of the hydrostatic data or hydrostatic variables like MCT, MCTC or TPC, displacement, the initial drafts, etc. Once you are given the position of the center of flotation, and once its distance from the aft perpendicular. So, once you are given all these parameters, you have been given the different formulas for calculating the change in trim. And once you find, and we have already seen that we always talk about, first of all, there is a parallel sinkage which we assume it to occur at the center of flotation, and then which is very straightforwardly measured by W by TPC, where W is the weight added. Now, once you have that change in draft, change in the mean draft, which we call as parallel sinkage, it is followed by the trim, which is a ship going like this or like this. And this we have seen what is the change in trim. Once you calculate the change in trim, total change in trim, how can we find the change in trim in the aft direction, in the aft point? How can we find the change in trim in the forward point? Just by taking the ratios of similar triangles, concept of similar triangles. So, we find the change in trim forward, aft, and once you find the change in trim forward, once you add the from the initial draft, you may add the change in trim forward and you add the parallel sinkage, you get the final draft forward, final draft aft. These are different things associated with trim. And then in trim, we also saw, after trim, we went into the concept of again dry docking, how dry docking also affects trim, and then we came into the bilging process. Now, this bilging process is much more important in a way than probably even the concepts of trim and dry docking. And so, we talked about how the flooding can be measured by using the methods of the method of loss buoyancy or the method of added weight. Both of these methods can be used for calculating the amount of the change in draft. And you also studied, we also looked at how there can be a change in the heel or trim again of the ship due to the flooding. Since flooding is a phenomenon that is unavoidable in nature in real world, which means anytime you commission a ship, you are certainly assuming that at some point or other in the future, the ship is surely going to come across a situation where it faces some kind of rupture, some kind of damage, as a result of which there will be flooding in some compartment. And so, it is very important that you be able to properly quantify what is the amount of flooding anywhere in the ship, what happens when there is a flooding anywhere in the ship and how it will affect the general characteristics of the ship. Now, so once you have flooding occurring, flooding which we also call as bilging, once you have this bilging occurring, these are all damage stability conditions, damage stability scenarios. So, once you have this damaged stability, or when you have that, we have seen using the method of Blaw's buoyancy how we can find the heeling. This will occur if the damage or the damaged compartment is not exactly center line, but it occurs probably towards one side of the ship, or in the case when the damage is not in the midship section, but occurs towards one side, whether it is a forward or the aft side, then you end up with what we call as what we have seen as trimming conditions. Now, one possibility. So, the only formula that you have to know to do this trimming condition is that, so in this particular case, when one end of a compartment, for instance, gets damaged, the only thing you need to know is you need to find, finally you are going to use the formula, the final change in trim. So, we end up finally we are going to use the formula change in trim is equal to the moment causing trim divided by MCTC. Now, MCTC will be given, the moment to change the trim by 1 centimeter, that will be given, and so the problem comes down to finding moment that is causing the trim. And in this case, if you remember the discussion in the last lecture, we have shown that it is important to remember that trimming always occurs about the center of flotation, that is that center line about which it pivots, that pivoting point is actually the center of flotation. So, at that point, so if you take the moments about, so the way to find out what is the rotation is obviously to find out what is the net unbalanced moment acting on it. So, we take the moments about this pivot, which is the center of flotation. So, in this ship, if you take the moments, we have seen from the previous figure something like this, you will have, okay, it was a box shaped vessel. So, if you assume that the center of flotation is somewhere here, if this is the length of the vessel, whole length of the vessel, and if you have the center of flotation here, then the net weight is going to act here, somewhere here, which is at the center of gravity. This weight is what is causing the moment. So, so the net moment is caused due to this weight, which is W, and therefore, the moment caused is W into the distance between the center of gravity and the center of flotation, which in this case we can write as something like this distance. We are talking about this distance, this. So, W into this distance, let us call it small l, this small distance L divided by MCTC will give you the change in trim. So, this C change in trim will be given by W into L by MCTC. So, what you need to know is the weight of the ship and the distance between the center of gravity and the center of flotation. For instance, you might end up with a problem like this. So, this problem states that there is a box of length 180 meters and breadth floating at an even keel, it is given as a draft. Now, find the draft of the vessel forward and aft if the empty full breadth compartment of length 12 meter is built. Now, what this says is that in this problem, a compartment here, if you look here, a compartment here which is of length compartment of length 12 meters, what it says is that a compartment of length 12 meters gets flooded here. Now, if you remember the previous class, we saw that this distance between the center of flotation and the center of gravity will be equal to this length divided by 2. So, it will be 6 meters. So, in this case L will be 6 meters, and now it is very easy, the problem becomes very straightforward. all you need to do is, so L is given, W is the weight of the ship, it is given, I mean it is not written here, but it is given, the vessel's displacement has to be given, otherwise you cannot do the problem. Now, once you have that and given the MCTC, you just find the change in trim, then you find the, so once you are given the change in trim, so once you find this, you go and do the change of trim in the aft condition. That also we have done. It is equal to the distance between the center of flotation and the aft perpendicular, the distance between these two divided by L into the change in trim. This will give you the change in trim aft and the change in trim forward. Change of trim forward is the distance between the center of flotation and the forward perpendicular divided by L into change of trim. So, using this formula you can get the change of trim forward and the change of trim aft. Now, with the change of, once you are given the change of trim, you add it to the initial trim, you will get the final trim, but in add or subtract, that is the only slightly confusing thing here, that is, so that is if you have the means in this case you need to find out whether you need to add the initial trim or the change in trim to the initial draft, or should you subtract the change in trim from the initial, that you need to check, that is. So, what you need, what is the easiest way to do this is, you can see where the load is added. For instance, in this problem you can see that the ship is bilged in the forward, it is given in the full forward, in this problem it is given the, it is given here, but it is that the problem is that the ship is bilged fully in the forward compartment. So, if it is given that the ship is bilged in the forward compartment, what it means is that this is fully bilged, and therefore, if this is flooded, it comes with automatic common sense that you can immediately deduce that this must be sinking like this. The ship at that point, okay, the ship should be, if this compartment is bilged, if this is filled with water, then it automatically follows that this ship should be sinking like this. So, what do you do to get the final draft? So, the forward draft at any point will become the initial forward draft plus the change in trim forward. So, once you add these two, you will get the final draft forward. On the other hand, how will you get the final draft aft? You have the initial draft aft, you have the change in trim, from the aft draft you subtract the final, you subtract the change in trim aft, you will get the final draft aft. So, each problem, instead of following just the mathematics, if this concept is followed, for instance, just check, that is, you see where the weight is added, if a weight is moved from the aft to the forward, for instance, I mean I am not, this is not dealing with bilging. In case of a simple transfer of weight, when the weight is transferred from aft to forward, it automatically means that the forward side will trim down, its trim will increase, that we measure, we usually say the ship trims forward, trims by the forward direction. So, that is and the reverse, if the weight is transferred back or if a weight is added in the aft, then the ship will trim by aft. So, it will go down at the back side. So, the draft here at the trim side, the back side will increase, the draft there will decrease. Now, the same thing actually it can come in mathematics as plus and minus if you are very careful, that is definitely a good way of doing, but each problem it is better to always, like if you have the proper positive and negative, you will get it as should the ship trim forward, it should the draft increase or decrease, but the best option is always to follow the logic and say that where is the weight being added, you just check that where is the weight going, is it going in the forward side or the backward side, I mean, or in case of bilging you say which side is getting bilged, is it the forward side or the backward side, I mean is the forward side or the aft side, and once you know that it is this or that end, then you decide whether it should go down or go up, and similarly whether the change of trim should be added to the initial draft or subtracted from the initial draft. So, this is the way to calculate the bilging process, and we have done most of the problems related to bilging using the method of loss buoyancy. As I have said before, you have to note that there is no difference in the final logic of the two methods. Both are following a similar trend of logic, except that in one case weight is added, center of gravity shifts, and the you assume that the total weight of the ship changes, whereas in the second method weight of the ship is not changed at all. Second method means method of loss buoyancy, the weight of the ship is not changed, the center of gravity of the ship does not change, but the volume is lost from the ship, area is lost from the ship, as a result of which I, which is the moment of inertia of the water plane, can vary, and the volume varies, the area varies. So, these calculations have to be borne in mind. So, these the assumptions that go into doing either of the method of loss buoyancy or the method of added weight, you have to have these, the basic assumptions should be clearly in the mind when you are doing the problems, otherwise it is easy to make errors. So, this is it as far as mostly bilging is concerned, and so in this lecture we are going into I think we are completely finished or wrapped up the section on trimming, anything to do with trimming, healing also more or less, and we are now going into into the final sections of dealing with regulations. For instance, today we will go into the different safety regulations and maritime laws and maritime regulations, which deal with the different concepts of stability parameters, which say whether the ship is stable or not, and this different set of rules based on which different classification agencies like IRS, that is the Indian Register of Shipping, or the American Bureau of Shipping, or the Bureaus Veritas, any of them, or Lloyd's Register, all of them, how they all have their own set of rules adapted from a fixed set of code. Now, first of all, there are some standard codes from which they have adapted their own rules and made it more detailed and more fine tuned to their situations and to their countries. For instance, like Indian Register of Shipping has rules specifically made for ships in India, it is more tailor made towards that country. So, like that we have. So, what we will do today, we have completely wrapped up the other sections on, in a way, most of the real theory part on stability calculations, which we usually call as the statical stability curves, the dynamical stability, and the different multipliers, means Simpson's multiplier, trapezoidal multiplier, and then the different concepts of trim, healing, and all that is more or less wrapped up, and we have come to an end of that, and rest of it is more towards laws and regulations, and of course, some more parameters on waves and some resonance. So, we will that is the rest of the lectures on. So, today we will go into what we call as the safety regulations, some of the important regulations that are followed in different parts of the world. We will, as I said before, we have a fixed set of rules that are given by the IMO. Okay, let us go into that. Now, the main organization that deals with the law governing is known as the IMO, which is known as the International Maritime Organization. So, I will just read this. The Maritime Organization was adopted in Geneva in 1948. Now, these are the people who deal with, who deal with the legal matters, environmental concerns, maritime security, they deal with even that, but their main work is to frame rules leading to the safety of ships. This one, safety, this is their main thrust area of work, but they deal with all this environmental concerns, which what they mean by that is they call it as our purpose is to make a safe shipping in a clean world, in a clean oceans. They call it the clean oceans, and so the different things they are dealing with, mainly they deal with IMO, the International Maritime Organization. So, they deal with, it is based in UK, in somewhere in UK, and It is a part of the United Nations organization. It is a branch of the United Nations. It is a council by itself, and they have about 159 or 160 member states, member countries right now, and these all of them come together, and all these engineers and the engineers and scientists and the top research people, they come together with the law making people or the politicians. They come together to frame the laws to make the to make the shipping safer and more efficient. So, these are so we will be dealing with the set of the framework of rules that are fabricated by the IMO, and mainly it is the rules are initially fabricated by IMO, and they have been adapted by different navies, mainly the US Navy is US Navy, the UK Navy or the German Navy. Of course, these are the three main, since these are the three main three most powerful, one of the three most powerful countries, we will deal with some of the rules associated with them, and we will see how the different criterion or the different problems that are faced by the shipping industry as such, these people, how do they tackle it. How as you will see, most of the rules are very similar. There are no differences, there are not much differences, but slightly adapted for their country and for different slightly different situations, and it is that just some differences in the way of approach. Now, usually the ships are classified into many different types. You will see that in general naval architecture we call them as cargo ships, container ships, tankers, passenger, ferry, then different types of like fishing vessels, or you will have tugs, then you will have mobile offshore drilling units, and you can have what we call as dynamically supported crafts, DSC, that is one special class of crafts on its own. They are some kind of unconventional crafts, the others are all what we call as conventional crafts. Now, there are the rules. We have already seen some of the rules associated with ships. We have already seen some of the basic rules that are followed in the few lectures in the middle. We talked about the different rules associated with the ore carriers. We saw how the ore carriers have their own rules and what are the conditions that are important in dealing with these safety of these ore carriers. We said grains and ores, it was actually grains. So, grains and ores follow the same principle. So, grains and ores, they have a fixed set of rules on their own. We have seen what are the rules associated, how is the how the shipping industry deals with the concept of wind stability or the resistance to wind, or how the industry adapts, how the industry meets this criteria, what are the conditions that the ships have to satisfy in order to satisfy the wind criterion. We have already seen how we took one distance, as if you remember, as there was a heeling arm developed as lambda 0, and we drew another heeling arm at 1.5 lambda 0, and we did some calculations similar to that. And it is very important to remember that all these calculations, all the latest stability rules are based on the concepts of dynamic similarity. And dynamic similarity, again, as we have already discussed many times, is to do with the area under the GZ curve. GZ curve we have already drawn, it is very similar, it is very common, it is very must be very you must be very familiar with that by now. GZ represents the writing arm, and it is a curve between the GZ, which is the writing arm, and phi, the heel angle. So, GZ phi curve is what we call as a statical stability curve, and if you do delta into GZ, delta is the displacement of the ship. So, a curve between delta into GZ and phi, the area under the curve is what we call as dynamic stability. Now, all the stability criterion are stability criterion dealing with dynamic stability. The importance of that was discussed many times. I will mention it again. The importance is that dynamic stability actually represents the energy in that condition. Now, delta is a weight and or it is a force into g z, that is a distance moved. So, it is like work done or energy content. So, it is the energy content, and so what are we assuming? When some energy, some form of energy is coming into the system, some form of perturbation, what we call as perturbation to the stability, some kind of force or some kind of phenomenon that is acting to remove the stability of the system, some kind of energy is input into the system to remove the stability. Now, when that goes into the system, how the ship reacts to it, or if that much energy goes into the ship, how the ship reacts without capsizing or without any permanent damage to the ship. So, this is the concept of stability. This is how we deal with stability. That is why this concept of dynamic stability is very important, because it does not matter whether even if the wind is in a gust, all we are concerned about is the total energy in that gust, and if that energy goes into the ship, if the wind hits the ship and the energy goes into the ship, or the wind does work on the ship again, which is like energy going into the ship, what will the ship do? So, the ship heels, will it go beyond some value such that it becomes unstable and capsize, or will it stay in a, will it come back to its original position. So, it is, whenever we are talking about dynamic stability, we will be dealing with area under the righting arm and heeling arm curve. Between the righting arm and heeling arm curve, that area under that area is what provides the dynamic stability, and that is what gives you the decides whether the ship is stable or not. Now, based on that background, we will go into some rules that are very important. The first of which is the set of rules dealing with passenger ships. Now, some of, as I have said before, it is always like this. So, you have the phi curve, that is the heel, and you have the GZ curve, and so let us suppose that you have a curve like this. So, this is what we call as the, and delta into GZ, if it is instead of GZ, if it is delta into GZ, this curve becomes the area under this curve becomes the dynamical stability. Now, always we draw the heeling arm as well. Now, the first rule of passenger ship says that between 30 degrees and 40 degrees, so this is 30 degrees, 40 degrees, the area under the righting arm curve, this area, this area should never be less than, it should not be less than, this is, I will write it here, it is called dynamic stability. It should never be less than, that means it should be greater than 0.055 meter radians. So, as you can see, the unit of the dynamic stability is either meter radians or tons meter radians. So, if you, this is obviously in terms of GZ curve, because its meter comes from GZ and radians comes from phi, it is the area under this curve. So, this is just, this is dynamic stability would be 0.055 delta, where delta is the weight of the ship. So, this is general, it says that the dynamic stability per weight of the ship, dynamic stability is actually delta into that. So, this it says that the area, so we cannot say exactly dynamic stability, but the area under the GZ curve, this area which is between 30 degrees and 40 degrees should never be less than 0.055 meter radians. That is the first rule associated with the passenger ships. Sorry, it is not like that. This area, the area, this area, sorry, slow, I made a small mistake here. The area up to 30 degrees, area up to 30 degrees should not be less than 0.055 meter radians, and area up to 40 degrees should not be less than 0.09 radians, meter radians, and this is the rule. And between 30 and 40, this area, between 30 and 40, this area should not be less than 0.03 meter radians. So, the rule says that, So, clearly the rule for this is the IMO rule for passenger vessels. So, the rule is that between the angle of 0 degree and when it heels between 0 to 30 degrees, within that angle of heel, that writing arm curve should be such that the area under the writing arm area under the GZ phi curve should be greater than 0.03 meter radians up to 30 degrees, and between and from 0 to if it heels up to 40 degrees, between 0 to 40 degrees it should be at least 0.09 meter radians, and also between 30 and 40 also it is important that there be at least a margin of 0.03 meter radians. So, this is the these are some of the this is very important as far as rules. This in fact is the backbone from which all the different rules associated with dynamical stability for different so the different dynamical stability for different types of ships modify from this. This is where it starts from. So, it is also important that the metacentric height GM0, GM0 is the metacentric height of the ship. You know that it has nothing to do with the angle of heel, it is 0, it is in the intact condition. So, GM0 should always be greater than 0.15 meter radian, 0.15 meter. So, this is the metacentric height. So, the rule says that the metacentric height of the ship should always be greater than 0.15 meter. Now, as we have already discussed, when you keep increasing the metacentric height, because this is an important thing we have already discussed, one thing that definitely should go home, you should take home with you after the end of the whole course, that is that the stability of the ship is in general measured by its metacentric height, and when you say that the metacentric height is large, you are in generally saying that the ship is stable, more stable. And so, we have said that and the moment metacentric height becomes negative, that is a case when G or the metacenter M goes below G, you say that the ship has become unstable. And so, GM it keeps becoming more and more positive, the ship in turn becomes more and more stable, that is true, but we have already seen that we cannot make it too large because the ship becomes too stiff to its rolling. So, when the ship rolls, it rolls like this if it is too, if GM is too high. So, we come to a case of we come to a situation of compromise between these two extremes of large GM and small GM, somewhere in between you try to bring it. So, the optimal GM which IMO has come up with is says that the GM0 of the ship, which is the initial metacentric height, should not be less than 0.15 meter. So, 15 meter is the, it is true for all kinds of passenger vessels irregardless of their dimensions. So, whatever be the dimension of the ship, whether it is 100 meter long ship or whether it is a 50 meter long ship, whatever it is, its GM0 should always be less than 0.15 meter. So, this is the one important rule associated with the passenger vessels, and it is in general recommended that it is also recommended that the maximum value of GZ, which is your writing arm, the maximum value of a GZ should occur at a value of heel angle which exceeds 30 degrees. So, you are not, they do not prefer you to have heel angles less than 30 degrees for their maximum GZ. So, the position where you get your maximum GZ in your curve, like here this curve, if you look at this, this is where you are getting your maximum GZ. This should always occur at an angle exceeding 30 degrees. So, somewhere here you should have the maximum. So, these are some of the basic rules from which all the series of regulations associated with the different kinds of vessels, cargo, container, or everything, of course, modified for that particular case, but this is the basic structure from which it's these rules. I think you should definitely keep it in memory and definitely keep it by hearted. It's something that is definitely important. As a result of this course, you should know this. Okay. Now, so once you have this basic set of rules, these are rules associated with the IMO, that is a maritime organization. Once you have these rules, there have been of course, these rules are framed mostly by the 150 organizations that go together to comprise the IMO, in which it is a fact that most of the work is done by US, UK, Germany and a few of the western nations. They are mostly instrumental in developing all these codes. Now, so they have sometimes slightly modified versions of this IMO codes. So, we will look at some of these important navies which have their own set of codes, they have developed their own set of codes. So, the US Navy for instance have a couple of rules, mainly there are of course, the whole book dealing with these regulations, maritime regulations is vast. There is many, it deals with ballast, it deals with environmental concerns, it deals with passenger safety, it deals with fire, the lighting of possibilities of fire eruption, everything, it deals with everything. But we in this course are since we are a course, this course is devoted to stability concepts, hydrostatics and stability. So, we will say that we will focus on those aspects of the code, stability codes. So, like we did with the dynamic stability, we showed the rules associated with that. So, we will deal with the stability concepts associated with wind healing. We have already given in some previous lecture, we have already told, I have already described how the whole set of calculations is done. I will just mention here the different laws associated with it. So, you have wind healing is a possibility, and you can have a healing due to turning, means when the ship tries to turn, it can end up with a healing, that is a healing possible. Whenever you have cargo handling means you shift a cargo from one point of the ship to another, either from the port to starboard side or from the forward to the aft side, whatever kind of transfer it is, it will produce its own healing. So, a healing moment is generated due to the transfer of cargo. It does not have to be cargo, it can be the passenger as well. So, the transfer of passenger also produces such a healing. So, these are the different types of healing moments possible, and each of these navies in fact have their own laws or rules associated with how to handle these kind of problems. And the basic rule for wind we have already given, I have already explained to you how the wind is done, how I explained that lambda 0, 1.5 lambda 0, and how we assume that the whole energy has gone into the ship, and how long the ship will continue healing with that energy input into the ship, how much further will it heal, like that I have already discussed. And turning, I have mentioned the basic formula of turning healing also, and some passenger healing we will take a look at now. Now, for turning, if you, I mean I mentioned this already, but what happens in the case of turning is, in case of turning, what really happens is that you have a force acting and you have a moment caused due to it. So, what happens is that when the ship tries to turn, in its centroid, exactly at the point of its kg, you will have a centrifugal force acting on it. The centrifugal force is given by m v square by r, delta v square by r, where r is the radius of turning. So, this will give you the moment that is acting to turn the ship. This gives you the force that is acting on the ship, that is the centrifugal force. Now, how do we find the moment? So, once the ship is trying to turn, so this centrifugal force causes the ship to, it acts on the center of gravity and causes the ship to shift in fact. So, the water in fact provides a reaction from the water provides a reaction, it tends to cancel the effect of this centrifugal force. So, the centrifugal force and the reaction from the water will cancel each other out, and the ship in fact does not really slide or shift in that fashion. So, and the vertical distance between the centrifugal force and the center of action of the reaction force from water is kg minus T by 2, where T is the draft. So, T by 2 is the point where the water reaction it can be assumed to act, and the centrifugal at kg. So, kg minus T by 2 is the distance. So, centrifugal force, the forces are the same. So, two forces acting and it produces a moment turning it to heel. So, this is the So, V 0 squared by r into kg minus t by 2 roughly gives you the net moment acting to turn the ship. Now, we can do some, instead of putting the velocity of turning, you can convert it by some shipping, you have some shipping statistics, you can say how you can convert it to V 0, which is the forward velocity of the ship, L is the length of the ship into 0.02, it is just some ship statistics. So, it has nothing to do with physics as such. So, this will give you the this is give you the momentum, the moment produced, moment trying to turn the ship, this is mt. Now, of course, this moment is provided by the rudder in turning the ship. So, the rudder provides that moment and the ship turns. Now, the rule associated with this is that this. Now, it is very important that the angle of heel does not exceed 15 degrees. So, we say that now, it is very important that the ship does not heel beyond 15 degrees as a result of turning. Whatever be the radius of turning, you are not allowed to take a turn that is more dangerous than producing an angle of heel of 15 degrees. Then heeling arm, now note that the moment divided by the weight of the ship delta will give you, actually in this, I believe this is not mt as such in this. This actually represents the heeling arm, not the moment to turn. Moment to turn should have a delta in it, that is your weight of the ship. So, once you take that mt divided by delta, it becomes this quantity, which is actually your heeling arm. So, mt divided by delta, that is which we call as the heeling arm in turning. So, the heeling arm in turning should be less than 0.6. So, the heeling arm in turning 6 meters, 0.6 meters. So, heeling arm in turning should be less than 0.6 meters. So, these are two important rules associated with the moment with the turning. Then there are some forms of rules associated with what we call as dynamically supported crafts. Now, since most of you are not familiar or not very familiar with naval architecture as such, dynamically supported crafts are crafts that have some other form of support rather than just the buoyancy force. You know that in case of ships, ordinary ships or conventional crafts, which we talk about, like of any kind of container ship or cargo ship, tanker or any boat, the weight of the ship, the weight of the boat or ship is balanced by the buoyancy force from the water. So, this is the Archimedes principle, the weights balance, the weight of the ship is balanced by the buoyancy force. So, this is the basis on which ships float, ordinary conventional ships float, it is the Archimedes principle upon which it floats. Now, it is possible that there are some other ways of actually balancing the weight of the ship rather than just the buoyancy force. For instance, you can put different kinds of hydrofoils. In fact, in the next lecture I will give you some pictures of hydrofoils, hydrofoil boats. These are kinds of boats which have hydrofoil is the hydrodynamic equivalent of an aerofoil. So, those who have familiarity with some aerofoil concept, aerodynamics concept, you will be familiar with what is known as an aerofoil, especially for those who have done some hydrodynamics or aerodynamics, you will know what is an aerofoil. So, there are flows over aerofoils, it can produce lift. You will, if you study that a little bit, you will see that there are different ways in which flow over an aerofoil can produce lift. It is due to just quickly I will mention it, that is, this represents, if this represents, this is a basic structure of an aerofoil and a hydrofoil is very similar in shape. So, we can say that this is a hydrofoil. So, this is the shape, if you call this to be the shape of a hydrofoil, what will happen is that you bring an air like this, if the air stream comes like this. So, this is a structure which remains like this and some air comes like this, or in our case we are talking about hydrofoils, we deal with water. When water comes like this, when it will come at some angle which is known as an angle of attack, and this will produce, because of the air which flows over the hydrofoil and below the air or water which flows above the hydrofoil or below the hydrofoil, this fluid, because of the difference in velocities of the fluid, differential pressure is created here and here. So, this region will end up with a higher pressure, lower pressure, this is minus and this is plus, lower pressure, and this region ends up with a higher pressure, and so this is a negative pressure and this is the positive pressure, which we call as, and this side we usually end up calling it as the pressure side, and this is known as a suction side or the phase and back, whatever you call it, and one side is at a higher pressure, one side is at a lower pressure. You know that when there is a, when any system exists in a continuum such that there is one side higher pressure and one side lower pressure, there is a tendency for a force to act from the region of high pressure to a region of low pressure. So, in this case there will be a tendency for a force to act like this. So, from this high pressure to low pressure force will act. This force we call it as a lift force. So, this concept of lift force, so this concept of a lift force comes into play in the case of a hydrofoil craft. So, in the hydrofoil crafts, because of the high speed in which it moves and the way in which it is designed, because of the shape of the hydrofoil and as such, it will produce a lift on the hydrofoil. Because of the circulation generated, it will produce a lift on the hydrofoil. Now, this lift in fact tends to lift the, let us call it a ship itself or a hydrofoil craft. That hydrofoil craft is lifted up as a result of this this hydrodynamically generated lift. So, it is due to hydrodynamic forces and not exactly due to buoyancy forces. That is the difference between a ordinary craft, a conventional craft, and a unconventional craft, which we call as hydrofoil boats or hydrofoil crafts. Even a hydrofoil crafts or a, so these kind of vessels are what we call as dynamically supported craft. It is supported by dynamic forces rather than static forces. Buoyancy is a static force because it is just due to the volume underneath, whatever is the volume underneath, and it is a static force. It has nothing to do with the velocity of the ship as such. It has nothing to do with the dynamics or hydrodynamics. It is only hydrostatics. It is purely hydrostatics problem. Now, therefore, this is the this is what we mean by a dynamically supported craft. Now, even a dynamically supported craft can have two modes of operation. We say that it can operate in two modes. We can it can be said to be operating in a displacement mode, or it can be said to be operating in a foil borne mode or a foil mode. The difference is the two methods I have already said. If the DSC, that is the dynamically supported craft, if the DSC operates purely using the concept that its weight equals buoyancy, Archimedes principle, if it follows that concept, then we say that the ship is in a, or the that craft DSC is in a displacement mode. If the ship operates such that its weight is now balanced by hydrodynamic forces, which are coming due to the lift due to the hydrofoil concepts, we say that the ship is operating in a foil borne mode. So, this is in general some basics about dynamically supported craft. Now, there are some specific rules for such, there are very many set of rules associated with such crafts, mainly because they travel at faster speeds and are more likely to be, and or they are more susceptible to accidents or disasters in fact. So, there are a lot of rules associated with that. Some of those rules we are not giving right now, but please remember that these are some rules, there are some special set, because we cannot mention all the rules in the short time that we have. So, we will we will broadly mention that there are a lot some similar these rules that we have already specified for the other type of crafts, that is the like we said, the passenger vessel, we have given a set of rules associated with the dynamical stability. Now, the same set of rules can be, there are some rules adapted like that for dynamically supported crafts as well, and these are some of the rules associated with the US Navy. Now, they have their own set of rules associated with wind heeling, for instance. That is an important thing. Now, they the no, I think I will go back to this. Now, the US Navy, they also have their own set of rules associated with the wind. The US Navy specifies that the wind lever which we call it as the heeling lever, the wind is associated with, it is usually given as PAZ by 1000 G delta. So in the previous definition, sometime back when we did the wind heeling arms, we talked about the general IMO rule, which is how the IMO generally states, which is the way in which IMO generally calculates how the wind stability, we say whether it is stable or not. Now, the US Navy has a slightly different way of dealing with the wind heeling arm. US Navy has a slightly different way of dealing with the wind heeling arm, and so we will go into that. So, first of all, what they say is that the wind lever or the heeling arm is given by this formula PAZ by 100 G delta. I will tell you what each term is. P is usually defined as a wind stress, and it is given a constant value of 540 Newton per meter. The meaning of this is something like a very high value, which is the maximum, for instance, that the ship can experience in the most violent weathers. Usually the most violent weathers come in regions of North Atlantic and in the Baltic Sea, somewhere in those regions you have the most fierce winds and most powerful winds, which produce the most dangerous conditions. So, we say that P, we assume in this P is assumed to be about 540 Newton per meter square. This is the wind stress. Then A is a characteristic of the ship. It is the windage area, which means the area in the ship which is exposed to wind. It is not just the total area, it is not important, it is the projected area. So, if the ship is like this, and let us assume that some region of it is above the water, and if wind acts like this, wind acts from this direction, it comes here, this area which is above, which is projected onto this plane. So, this area does not matter, it is only this area that matters. Project this area into this plane, you get the windage area. So, that is known as A, that is the windage area. Then Z is the distance between the centroid. So, if you have the windage area here, the centroid of that windage area to the T by 2, T by 2 means, again the concept is this, the wind acts at the centroid of the windage area, it can be assumed to act at the centroid of the windage area. The reaction from the water here can be assumed to act at the T by 2, half the draft, means the total force is acting over the whole draft, and if the force is constant, that force can be assumed to be acting at the centroid, which is at T by 2. So, the distance between this centroid of the windage area and T by 2, that distance is Z. So, Z is that distance. G is the acceleration due to gravity, and delta is the displacement of the ship. So, once you have this, you end up with the wind lever. So, you get the wind lever, and there are now a couple of formulas which give you what are the stability criteria and how the role of the ship is calculated as a function of this lever. That since we are out of time now, we will continue with that in the next lecture. So, we will stop with that today. Thank you.